My job is simple. I have to introduce our president, Ian Sloan, to you. And I'm going to say that it gives me great pleasure to introduce our friend, colleague and president of the Royal Society of New South Wales as tonight's speaker. Scientific Professor Ian Sloan, AO, FAA, FRSN, did theoretical atomic physics for his PhD, flirted with the real world, but switched to applied mathematics and is now an internationally recognized computational mathematician. He's won a number of prestigious prizes in mathematics and was appointed as an officer in the Order of Australia in 2008. What Ian does is summed up by the title of an ARC grant he received in 2011, a few years ago. Very high dimensional computation, the new frontier in numerical analysis. Some of us may remember his last talk to the Royal Society in New South Wales in 2014, when he explained the fourth dimension to us. Of course, he has now gone on to many, many more dimensions. His talk today will be a ramble through his interests, not just in mathematics, but reflections on the paths that careers can take. Please remember there'll be a Q&A during and after Ian's presentation. I shall be monitoring the questions and will ask them in the session after his talk. You'll find the Q&A button at the bottom of your screen, if you're lucky. Thank you now. Thank you. And now over to Ian Sloan, who will deliver the OGM lecture, Presidential Reflections, Science Stuff, and the President's Random Path. Thank you.
Well, thank you, Brendan. Thank you, Brendan, for that lovely introduction. What can I say? Well, as you've heard, I'm not only president of the Royal Society of New South Wales, which of course is a great honour, but I'm also a mathematician who started life as a physicist. And it has been a long path, and I would like to tell you, I'd like to reflect a little on that long path, tell you something about what I've learned along the way. And because it seems like a sort of odd path in many ways, I'd like to sort of show you what connects it. And so, okay, so now my task is to share my slides. So let's see how we go. Okay, so now, okay, so I'm going to tell you about some things I've learned along the way. And I just have to get it live this time. There we go. Okay, so I'm going to tell you first of all about random walks. The random walk, or the drunkard's walk. And I'm doing this for two reasons. I will give you a good scientific reason for doing it in relation to the things that I know and have worked on, but also some sort of metaphor for my own career. I hope not the drunken part, not entirely, but the random nature of the process. So let me tell you about random walk first of all. So there you see the random walker. He's starting at a certain point, which is where he is, what you see him right now. He's just had a swig of the bottle, and he's going to take a 1 meter step in any direction. And so he takes the direction that you can see as it happens. It's this one along here. And he goes 1 meter, and now he takes another swig. And by now he has lost memory of where he came from. So now he walks in a random direction. As it happens, he goes this way, another meter, and then he takes another swig and again loses memory of where he's going. So he moves 1 meter at a time in random directions, different processes, maybe paths crossing, maybe not, and eventually he gets somewhere. No, it's not, of course, he hasn't gone, if he has 100 steps, 100 meters, he doesn't get 100 meters away, but he does get away on, actually, this is a very interesting question in mathematics, in statistics, in physics. The random walk plays an important role, and I shall give you some applications shortly. And so, well, you can generalize this idea, not a drunken walker, but in physics, you can think about the walker as starting in the middle. He's starting in the middle of this cube. You understand that? Starting in the middle. Now, the green path is the first path that the random walker follows, and it happens to follow a very, very short steps now, lots of steps, but finishes up somewhere. What we're seeing here, though, is Of course, the random walk, it could be done different ways, right? If you come back tomorrow and ask the random walker to do it again, it goes in a different direction, makes a different decision. So one would say that's a different realization. The red one is a second realization of the random path. The blue one is the third realization of the random path. And you could, of course, go on any number at making, and you could see how to do this, of course. You can make a program that does it, simply tosses a coin at each step, and then you just repeat the process with new coins and new randomness. And so, okay, so I tell you now, important application, it's to Brownian motion. In 1827, Robert Brown observed pollen particles on the surface of water. I think Robert Brown became his fame rather easily, actually. He observed them under a microscope and observed that each pollen grain appeared to be following a random path. So what I'm showing you here is from a recent book, not Brown's drawings, but from a recent book of something similar. It's the motion of colloidal particles, small particles, on the surface of a liquid as seen under a microscope. And you see here three different pollen grains, their paths, and each one of them different, of course, because they each follow a similar path, and they each follow a random, not similar path, but they each follow the same principles. That seems that they're being knocked about by invisible forces, as we shall see. So Brownian motion, as far as I know, Brownian never did much about the theory, just observed the phenomenon. And why I say he got his fame rather easily is because he wasn't the first. He was 2,000 years too late. This is in the scientific program on the nature of things around 60 BC, before the Common Era, by the Roman philosopher Lucretius. And he describes the Brownian motion of dust particles in a sunbeam, you all see this in a sunbeam, moved by blows that remain invisible. And he went on to articulate what we would think of as an atomic theory of matter. So the Greeks, the Romans, and indeed the Greeks were very advanced in thinking about atoms. So Robert Brown was lucky to have such fame, I think. But Brownian motion, every scientist knows about Brownian motion. So I tell you about my own Brownian motion, if you like, as a career-wise random walk through a number of different topics. And I will touch lightly on atomic physics, nuclear physics, computational mathematics, high-dimensional problems, as been advertised, spherical games, astronomy. And I'm particularly interested to tell you not about the great triumphs we've had along the way, or what makes us famous, if we're famous, but rather about what connects all these things and what are the underlying ideas and what are the different cultures that one meets along the way, and indeed some of the interesting people that one meet along the way. So let me start by telling you about where it all started. So I managed to find in the dusty archives my first published paper. It published in the Royal Society, Proceedings of the Royal Society of London, and it's about electrons scattered by atomic hydrogen. And I would tell you just a tiny fragment of the science of such things, so I don't expect you to read the paper. Now, where it began was at University College London. I'd like to tell you a little about University College London because I think it's an interesting place and it has some interesting connections. So it was founded in 1826, and that's just 5 years after the foundation of the Royal Society of New South Wales. And it has, I think, a proud record. It claims to be the first university in the United Kingdom to admit Jews, Catholics, and women, who did not discriminate on the basis of religion or gender or anything else, which I think is a wonderful thing, and it makes you wonder about the others. Well, it is said to have been founded on the principles of Jeremy Bentham. Jeremy Bentham didn't have much to do with the foundation. Jeremy Bentham, a very interesting social philosopher, I suppose, social reformer. He had some very good ideas and some perhaps not so good ideas about open prisons, in which people were observed all the time, which is a bit of a terrifying idea. But the most interesting thing about Jeremy Bentham and UCL is that his body is not mouldering in the grave, but rather it's at University College London. And it's at University College because in his will, he prescribed that his body should be dissected, reconstructed, and given to University College London. So it's there now. It's in a corridor, and it's in let's see, his body is there, it's clothed. His face is presumably a wax image. He's wearing a hat, so you can't see his beautiful hair. But his body is evidently all there on view for everyone to see. Most of it's in the clothes, but his heart is said to be in the briefcase at his feet. So I always thought this was a wonderful thing at University College. I mean, it gave it a real touch of colour. And I can tell you a little story against myself that last year I happened to be at a workshop in North London, and it occurred to me that I have never been back to University College and I've never revisited Jeremy Bentham. He's just up the road and I could duck along and have a chat to him in his glass case. So I went I found where I was, I mean, with some difficulty. I found the University College. I found a door. It was locked. But, well, that didn't worry me because somebody came out, so I went in where the door was locked, and so I started prowling the corridors looking for Jeremy. I didn't find him. I ran out of time. I had to be back to give a talk. So I thought, well, I better get out of here. So I tried the door I came in. It was locked. I told you it was locked. But I forced the door. I just turned a little lever on the top of it, and it set off all the alarms in the building. So now there's a resounding clangor of noise in the building, and I am there stuck in the building and wondering what to do. I thought, well, if I wait here, someone will come along and talk to me sternly or arrest me or something, because in London they're very frightened of terrorists. So they will say, what are you doing here? And I will say, well, I'm visiting Jeremy Bentham. And they'll say, who's Jeremy Bentham? I say, well, he's that dead fellow along there. And so I thought, this is not good. This is not profitable. I should get out. So I found a quick exit. I made my non-random exit out through the loading dock, walked swiftly, not randomly, in a purposeful but calm way. And I'm sure that now I'm still on many cameras in this around North London, because, you know, there's CCTV everywhere. It's the most photographed place in the world. And they're wondering, who is this person who caused such trouble, this terrorist at University College London? Anyhow, so I go back to talk a little bit about what was I doing there. Well, I was doing scattering of electrons by hydrogen atoms. And there you can see this very sophisticated diagram that I produced, in which an electron, actually a beam of electrons, is hitting on hydrogen atoms. And if you've forgotten, a hydrogen atom consists of a proton, P, and an electron around it. The electron is in orbit around it. That, of course, is not a very good representation of a hydrogen atom, but it will do. It's in its ground state. And so the electron comes along and then it's scattered. And so what happens afterwards? Well, perhaps the incoming electron is scattered by the hydrogen atom and goes at some angle. That's interesting from an experimental theoretical point of view. Or perhaps the atom is left in an excited state, because hydrogen atoms, I hope everybody knows, they do have excited states. And or perhaps it's broken up altogether, and so you have just two free electrons and a proton at the end. And so we're trying to understand all these things happen. And I've said it looks simple. When I draw a picture like that, it looks very simple. And chemists, of course, do much more complicated things. But it's not easy. Scattering problems are not easy. And I quote the first sentence from the paper, which I think is quite good. The chief theoretical difficulty in slow electron scattering by atoms lies in taking proper account of the distortion produced in the atom. Well, that's very true. Of course, everything is reacting to everything else. But I might say if it was a fast electron, then physicists and chemists have easy ways of approximating things. You don't take account of the distortion. You use approximations due to Max Born and others. It all becomes easier. But when you want to look at the full dynamics, it's quite difficult. So I'm not going to tell you how it's done, but of course it's all governed by mathematics. It's governed by the Schrödinger equation due to Evan Schrödinger, who was a Viennese theoretical physicist, and is very famous for this equation, which is the fundamental equation for the whole of chemistry, you could say. It's about electrons around nuclei in general. And in this case I told you about, it's a differential equation with 6 variables, and I'd like to just explain to you why it is 6. What is magic about the number 6? Well, you can think the proton is infinitely heavy. Well, that's a physicist, a chemist approximation, right? They're very good at making physically based approximation, but think of it as infinitely heavy, so it doesn't move. So the electrons move. There's 2 electrons. Each of those needs 3, X, Y, and Z. It needs 3 variables to describe its position in space. So there are 2 of them. 2 times 3 is 6. So there are 6 variables. So in that sense, it's harder than having 1 variable, but it's a lot easier than having 10 or 100 variables. So let's go on. And now I've moved on a long way in science. I've moved into nuclear physics. And by the time I was at UNSW, well, after I was at UNSW, I started working on the problems of neutrons being scattered by deuterons. So this thing here, a neutron and a proton stick together, form a bound state of a deuteron. So that is a deuteron. And chemically, it's just like a proton because a neutron doesn't have any charge. So chemically, it just has the same effect as a proton, but it now is different from this point of view because we're not interested in the electron. Think of the electron far, far, far away. But if we're looking at what happens at the nuclear level, and the problem is the same, right? It's still the same 3-body problem. Well, it's the same, but it's different. First of all, it's published in different journals. I mean, it's culturally completely different. Atomic physicists and nuclear physicists, by and large, don't talk to each other. And they publish in journals with different names. So nuclear physics, for instance, is a good place to publish this material. The masses are all the same instead of being very different. Still a 6-variable problem because if you want the science, the center of mass of those 3 equally sized, equally massive particles doesn't change, is not interesting. And so it's only 6 remaining variables. Yeah. But anyhow, so that's the connection between those things. And now I'm going to move even faster along onto new areas of computational mathematics. And I put up a health warning that an integral equation is approaching, which many people will consider very dangerous. And on this slide, I am going to show an equation. So it's the top equation there, and I've got a good reason for showing it. You don't have to understand what it means, but so it contains, it's first of all, it's an equation. It says equals, right? There's an equal sign in there, and everybody knows what that is. But on the right-hand side, there's some f, which is a known function. F of x is a known function. I give an example. K of x and y is a known function of 2 variables, and I give an example. The important thing is that the u is an unknown function. It's a function of x between 0 and 1. And the real point is, this is an equation. It appears on the left, and it appears on the right. How do you find the solution? Well, I can tell you that, except at high school, you don't find a solution analytically. There are no simple solutions. You find it computationally. And everybody, people who work in these things, know that that's what you have to do. Solving equations is what a lot of people do. In our nuclear physics world, we were finding approximate solutions of equations just like that. Well, more complicated. They have 6 variables, not just 1, not just x, but 6 or more, depending on the problem. But so we're already solving such problems. And I think this is interesting that physicists, chemists are wonderful at approximate solutions of everything, but there is a big difference in approach, which I found interesting and I would like to try to explain to you. So here I go in my attempt to do this. In physics, you have that equation. Suppose that was the equation as a model of your problem you're actually wanting to solve. The physics, the question is, can I find a better approximation? And so what you do is you find a good approximation of this right-hand side of the integral there. It's an integral. And I haven't told you how we approximate it. That would be definitely not appropriate for this evening. And that's not the point. But you approximate it in some way. And to show that, the physicist will write this funny symbol here, this wavy, the parallel waves, you could say. It means approximately equal to. A physicist will always write approximately equal to. UX is approximately equal to this thing, to whatever we've done on the right. Now, in computational mathematics, people think about it the same way. The first question is, can I find a better approximation? But the second question is, and what's the error? And can I prove that the error is small? And so they said about it in a different way, which I will try to explain. So please don't stay with me, because the health is still in good shape. In computational mathematics, you would always think about not just one approximation, but a sequence of them. And why? Because the first one is good, the second one is better, the third one is better still, and so on. You keep looking for a sequence with getting better and better approximations. So n goes up to 1, 2, 3. And the nth approximation I will call u sub n of x. It's a function of x. But I call it u sub n of x, and it occurs on both sides. And the really crucial thing is that here we have equality, not approximately equal, but equals. So this actually defines un. It doesn't tell you how to find it, of course. That's another question. That's another question. That's part of computational mathematics. But it is well defined, the approximation. And that allows you to say that the error is ux minus un of x. It's the difference. In physics, what can you say? The error is ux minus approximate ux, but there's no special symbol for it. You see, it's all just the same. So it's that I never saw in physics, I never saw anybody write down a definition of the approximate solution. So there's a real cultural difference. And in that sense, I would say physicists and chemists, Bren, this is just for you, the chemists, physicists and chemists are wonderful at imaginative ideas for finding good approximations. But they never tell you how good is the approximation, because they don't, in some sense, have a mechanism for that. Or maybe they've lost interest by now. They know they're right, and they don't need to worry about what is the approximation. I just said, I found the cultural difference the hard way, because when I was working in physics around about the mid-1970s, I thought, we're doing interesting things. There are so many interesting ideas around here in physics. I will write it up for Mathematics of Computation, a good journal. And what I found is that when I wrote it up, submitted it, my beautiful work, these beautiful ideas, they didn't like it. They didn't like it. I was shocked by that. But they wanted me to rewrite it, which I refused to do because I've always been stubborn. But anyhow, I submitted it elsewhere to the Journal of Computational Physics. That is a middle ground. But in the end, I had to learn how to do things the computational mathematics way and then prove things. How do you prove things? Not just a good idea. How do you prove that it's a good idea? And you prove it by showing that the error is small and that it's getting smaller, and you say how big it is. So that's what we do. That's what we do in computational mathematics. We tell you that we prove that this is a good method. The error is small. It's going to get smaller still if you do more work, and we tell you how small that will be. So that was pretty hard. So let me move now to an easier situation, easier problem with hundreds of variables. So in physics, we often have to handle problems with 10 or more variables. So it's natural to be worried about how you handle even more variables. And around about the 1980s, a friend of mine in nuclear physics, by this time I was not anymore working in nuclear physics, but they introduced me to some new ideas that they'd heard about and discovered in the literature, the wonders, I say, of methods based on number theory. And number theory is the branch of mathematics concerned with whole numbers, prime numbers, for instance. Is there a largest prime number, for instance? That is a good question. How many primes are there as you get to bigger and bigger numbers? The answer is, of course, there's no end to the number of primes, but how many prime numbers are there in an interval? And, well, many, many interesting questions. It's an important branch of mathematics, fascinating one. I don't know much about it. I'm no expert, but as in many other areas, I'm a bit of a user of it, and I became hooked on these methods. And so I will spend one pictorial slide in telling you what it is to work in 100 dimensions. But I cannot draw a 100-dimensional picture. So what I'm doing is to show a problem with two variable dimensions. Excuse me just a moment. Nothing works now. There we go. So this is a problem with two variables, and those of you who know any mathematics, I'm looking at this Mexican hat as a function as a function of two variables, x running up here from 0 up to 1, and y running from 0 up to 1 the other way. And it's a function of two variables, and it could be anything. It could be the temperature on a heated plate, for instance. And so my problem is to estimate the volume under that hat. You can cut it up into little pieces and put in little bits of stuff, and you can try and do it. But one way to do it is to compute the average height over a number of points. And here I've chosen 64 points randomly. So the points are the bottoms of the sticks here, and they've been chosen randomly in this square. And we do this, we take the height at each of those points, the height up to the surface, we average it, because the total area is 1, so that makes sense. We just average it. And here the points are chosen randomly. And that is one way of really doing things. That is one real way of doing things. It's called the Monte Carlo method. Reflects on gambling randomness. But Monte Carlo is a very good method for doing things, but it's not the best method. Number theory tells us how to do it better. Even if now it tells us it don't need to just two dimensions of two variables. You could have 100 variables or 1,000 variables. And you can use Monte Carlo, or you can use another theoretic methods. And you can use thousands of points, not just 64 points. So anyhow, that's my introduction to high-dimensional problems. And that's all that we're going to do about high-dimensional problems. And I thought I would tell you about the personal side of this in some way, that my main collaborator in high-dimensional things, I don't mean high collaborator, my main collaborator in high-dimensional things has proved to be Frances Kuo, whose picture I show here. And I will tell you just a little bit about her story. She was born and educated in Taiwan, moved to New Zealand to do a PhD, and it came to me, a short story, she came to University of New South Wales as a postdoc, and been there off and on in different ways for 20 years, and is now a full professor, and a well-deserving, very talented person. Together we've published 40 papers or so, but the first, the first was together with my former student, Stephen, who was her supervisor. So she is, they would say in Europe, they would say she is my doctoral granddaughter. She was supervised by the person whom I supervised, Stephen. And she is a mother and a very hardworking, very capable, very intense collaborator who pushes me very hard. Now, one of the things that makes this life difficult in this high-dimensional things is what is called the curse of dimensionality, a colourful phrase, I think you'd agree, coined by Richard Bellman in the 1950s, who was a colourful character in mathematics. The curse of dimensionality describes the extraordinarily rapid way in which problems become more difficult as you get more and more variables. And, we have the curse of dimensionality, yet nowadays we often want to solve problems in hundreds or thousands of dimensions. We have actually once resolved a problem with more than 1 million variables, and quite successfully. And so the question, this has been a tricky thing, a long time, a difficult question for many people over a long time. And perhaps we made some progress on this in work that I've done. Another of my favorite collaborators, Henryk Wojnarowski. We started in 1995. And he asked a question always, that what happens if we change the dimension, the number of variables, if we continuously increase, well, not continuously, but if we increase the number of variables, and this is another cultural difference, that somehow this was a question that at that time never seemed to be asked in computational mathematics or in number theory. A lot of the big advances were made by number theorists, but they always say you could have, well, any number of variables as long as it's prime. For instance, prime number. No, we don't need a prime number. I take that back. We have any number of variables, but the answer, the errors would depend on, in an unknown way, on the number of variables. The constants would depend on dimension, and nobody ever worried about the constants. So the problem could be it could be easy at 10 dimensions, getting to be impossible with 12 dimensions. But Henry was always asking, what about the constants if we change the dimension? And this was a very profitable line of are you showing me something, Judith? No. This was a very profitable, a very fruitful line of questioning, because we did manage to do some interesting work on this, which has attracted a lot of interest. We were able to show that in many normal settings, the problems are indeed intractable. That is, they become, may say, exponentially more difficult as you increase the number of dimensions. But on the other hand, if the problem is somehow easier in successive dimensions in a controlled way, then it becomes possible. And we have found that many problems can indeed be done this way, particularly applications with Francis. And I'm going to tell you about one application. This is just on one slide. It's one application, but it may require more concentration than most things. So it's a problem with possibly hundreds of variables, so you will know that such problems do arise. It's the problem considering the flow of contaminated water through rock. It is important because if you are trying to contain underground water, contaminated water in the from nuclear waste, you want to know how soon it will get out into the underground water. But describing all the channels in a piece of rock, or all the tiny bits that carry water, is really too hard. So it's common engineering practice to model the permeability. That's the ability of water to flow through under pressure. To model the permeability as a random field. And what's a random field? Well, I've said at the bottom, a random field is like a random walk. Mathematically, they're very closely connected, only it's not just one path. It's more like a spread out thing, something that fills space. And so the mathematics is very similar. And I show you a picture of a random field. Well, it's not really a picture of the random field. It's one realization. It's a picture of one realization of the random field. Because if I ask for another one, if we start the random walker again, we get a different realization. And if we start it again, we get yet another one. But they all have some similarities. And you can see here that it's like a random walk. That what happens between neighboring points, you might say, it doesn't change so much. It doesn't go so far in one step. This is all sort of connected in some way. Anyhow, it might take 100 random variables to describe this random field. And in that case, you have a flow problem with 103 variables. 3 for the space dimensions, you see, and 100 for the stochastic dimensions. So problems like this are now the big news in computational mathematics, often under the heading of uncertainty quantification. Uncertainty quantification. Anyhow, enough about that. That problem was introduced to me by this person, just to introduce some personalities into it. Ivan. Well, Ivan told me about this at a conference we were at in 2007. I'd never heard of the problem. I knew about high-dimensional things, and he thought it would be good for us to get together. Now, it was not for the first time, because Ivan, in fact, was a PhD student of mine at the University of New South Wales in the 1970s. He was my first student in computational mathematics and is, again, a valued colleague and collaborator and a really nice guy. Okay, so another problem, I'm getting near the end of my problems, is how to place 100 points uniformly on a ball. Well, here's one way. So this, the pictures are calculations are due to my friend Robert Womersley at the University of New South Wales. This set of 100 points It minimizes the electrostatic energy if the 100 particles are electrons on a conducting surface. You know, electrons repel each other, so they move as far away as they can from each other. And if you let them be static, then they have no, if they're not moving, they minimize their potential energy, the electrostatic energy, and they form some configuration. Now, this question is an extremely important question in physics, in mathematics. It's known as Thomson's problem. What is the configuration of electrostatic particles repelling each other? And there is no simple answer. There is no such thing as a uniform distribution of points on a sphere. It's a strange thing, that, because the next level down, the problem the next level down, is how to distribute points on a circle, not on a disk, just the frame, just the boundary, so on the circumference of a circle. Of course, you know how to do that. You just divide up the circumference into equal lengths and put one point at each of those. It's easy. You can divide into 100 points, any number of points. On the sphere, there is no simple answer, and I can assure you that some of my friends, Ed in Nashville, Tennessee, spent essentially his life working on the mathematics of energy minimization in its different forms. So there is no simple way of doing it. I'm not telling you quite the truth, because there is one situation. Oh, excuse me, I've forgotten. I needed to show you the coronavirus view of these 100 points. That's, of course, a terrifying image, because it is reminiscent of the corona out there. But I have a reason for showing it. It is, look, I'll tell you what it is, first of all. If we take 100 points, that's 100 of these spikes there, and fix the electrons, and then we put on another electron, which of course is repelled by all of them. But if it gets close to any of the static points, then the electrostatic energy gets very high. So this is a picture of the electrostatic energy of 101st particle electron moving against the 100 fixed ones. But I have another reason for showing it. It reminds me that, you know, I should be making the point as I go along. Perhaps you picked it up already, that mathematics is everywhere. Actually, the whole of theoretical physics is completely mathematics, and same of theoretical chemistry. Sorry, Bryn. But also, you will have all learned in recent times that in epidemiology, it's all mathematics. I've never seen, as in recent times, so much mathematics on the television. All this flattening of the curve is about the differential equations that control the populations and so on. So it's there in a big way in modern biology, and that's something that I ought to be emphasizing. So the exception to where it's easy to put points on are the vertices or face centers of the 5 platonic solids. So they are, of course, beautifully arranged on a sphere very regularly. But unfortunately, there are only 5 platonic solids. And in physics, we often needed to integrate over all directions in space. That's why we needed all these things. But we needed many well-placed points on the sphere, many, many more than you have from the platonic solids. So the platonic solids are beautiful, but not very adequate for computation. I wanted to go from this small number of points to 50 million. How about putting 50 million points on the sphere? I've only recently learned this because as I've been moving around on my random path, I've got connected again to astronomy. People in astronomy use what are called Hilpex points. The H is hierarchical, and I show you how they're done, roughly speaking. So there are hierarchy. The green points here, there are only 12 of them. They're put in the center of 12 regions of equal area that make up the sphere. There's one point in each of them, you can't see them all, but there are 12 points there in the green thing. Then you divide each region, or each green region, into 4 parts and put one point in the middle of each of those, and that gives you the yellow set of points. There are 48 of them, 4 times 12, and then the red 192, and the blue there are 768. And by the time you get to level 12, there are 4 to the 11th times 12 points. There are 50,300,000 and some number of points. And they are really used. And I will show you now a picture that uses all those points. and it's from astronomy, which is one of our recent interests. And why? Because we're interested in points on the sphere. One thing, we're interested in the sphere because of its directions and so on. This is the cosmic microwave background radiation. It's of enormous importance in cosmology. It's perhaps now considered the leading evidence about the Big Bang, about the origin of the universe. It comes from the cosmic microwave background. This is a picture from the Planck satellite data. A satellite was up there for quite a few years, put up by the European Space Agency. And I'm going to just try in a moment to tell you what it is that we're looking at here. We're first of all looking at a picture of, we're looking from Earth, or near Earth, from satellite, at the whole sky. It's the whole sky mapped into one flat piece. Of course, to do that, you have to sort of cut the sky somewhere, so it's sort of cut at the edges, flattened out. But that's what's been done to this in a very precise way that preserves areas. So it's a picture of the whole sky. It's a picture of the electromagnetic waves coming in, which come from a hot body, a very cool body, actually. It comes in as we measure the temperature. What's measured here is the small variations in temperature from the average thing. So this black body radiation was discovered in the 1950s, actually discovered by people who were trying to work out what the heck was this noise that they were hearing in their amplifiers. And it turns out to be something that's always there. It comes from all directions, but it does have small variations. And it's those variations tell us about the early history of the universe, about the creation of the universe. So these variations are of enormous interest. So the astronomers look at that. Their theory is that, well, leaving aside to a first approximation, this is one realization of a random field with very particular characteristics. And is it a random field? Well, it's a bit like the one I looked at before. You can see that what happens in one region is correlating. What happens in one place, for instance, this blue place, is strongly correlated with what happens nearby. So the correlation is of great interest. It's not just all over the place. It's like a random walk. It's not all over the place. It doesn't go suddenly from Sydney to Brisbane. It is closely connected to everything that's nearby. Our interest is, well, first of all, can we approximate this thing? It's difficult to approximate because it's so bumpy, so varied, such a small, short scale. But this is something that we're very interested in, computational mathematics. And second, is it really a realization of a Gaussian random field? Well, we've developed a tool for analyzing such things, which I don't tell you about, but that's our current interest, and we are currently trying to get this work published. So it's enough about that. So before I just leave my own path, I thought I would just tell you what I have learned about the secret of having a long path. I mean, because that's something I can claim to have done. Right? I claim more than most people to have been at it for longer and to have been able to continue. I'm still actively researching in high-dimensional things on those on the cosmic microwave background radiation and other things. So what's the secret? Well, I've boiled it down here to three things. The first is don't keep digging in the same hole. If you keep digging in the same hole, you will eventually run out of good ore in your hole. Cultivate widely. It's a bit that the metaphor is of the miner versus the farmer. I must say I'm a farmer. Be willing to learn new things, because if you don't learn new things, you will never be able to move from where you are. And the third thing is be a good collaborator. And I've mentioned some of my collaborators deliberately because I think research in mathematics, in mathematical kind of things, in physics, is a human occupation and one that is much more interesting because it is a collaborative venture. So before I finish, I want to duck back to just to look at astronomy again, but 199 years ago. So this is I was found in Journal 1 of the Proceedings of the Royal Society of New South Wales. This is a paper on the astronomy of the Southern Hemisphere. It presented read on the 13th of March, 1822. That's about 9 months after the establishment of the society, and its first version was the Philosophical Society of Australasia, which seems to be misprinted here, but it's certainly before our society, and it's by this guy called Dr. Charles Stargard Rumka. And of course, the immediate question is, well, who is this Rumka doing astronomy of the Southern Hemisphere so early? I might just tell you that astronomy of the Southern Hemisphere is extremely interesting to astronomers, because I don't know whether you know this if you're not an astronomer, but the southern skies have 2/3 of the interesting objects of they're far more interesting than the boring Northern Hemisphere. The nearest galaxies, the two Magellanic Clouds are seen in the Southern Hemisphere. The center of the galaxy is up there near the Milky Way. So you see so much more of the Milky Way from the southern skies. So now, who was Charles Rumka? Well, I tell you a little about Rumka. He's famous. His name was actually, well, one of his names was Karl Rumka. He was German. And I learned this from the Australian Dictionary of Biography. He was an astronomer. He came in 1821. Well, I mean, he wasn't really an astronomer at that time, but he came with Thomas Brisbane in his entourage. Brisbane was the 5th governor of New South Wales, and I'll have a little more to say about him. Rumka discovered the reappearance of Encke's comet. It was only the second observed returning comet. It had been predicted by Encke. But Halley's comet, of course, as you know, returns after some period. That's 80 years from memory. Encke's comet is also a returning comet, and only the second one observed predicted. So the fact that they did find it again was really something. And he did this at Parramatta. He did this at the Parramatta Observatory. Did you know about the Parramatta Observatory? It's set up by Sir Thomas Brisbane. Rumka was a colourful character. He fell out with Brisbane. He fell out with his colleagues at Parramatta Observatory, and but nevertheless went on to have a distinguished career in Australia. He became government astronomer. So important, of course, in those days, you know, about timekeeping and everything else. He later won the gold medal of the Royal Astronomical Society of England. And I tell you now just a little about Brisbane. Now, Brisbane was a military man, governor, and astronomer. Actually, even more famous astronomer. The 5th governor of New South Wales. He followed Lachlan Macquarie. He was here only 4 years. And I think it's fair to say that he was a much more successful astronomer than he was governor. He wasn't sufficiently diplomatic. He brought with him astronomical instruments, telescope and so on, and 2 assistants, and set them up at Parramatta, made the Parramatta Observatory, where internationally important observations were made. Brisbane won the gold medal of the Royal Astronomical Society, became a fellow of the Royal Society of London, and for 20 years or so was president of the Royal Society of Edinburgh, after which we are much modelled. Brisbane was first president of the Royal Society of New South Wales. He took up the position as soon as he arrived, and I think that's something proud. I calculated, I went through our records, which are on our website. I urge you to look at the website. And I have counted up that I am the 118th individual to be president of the Royal Society of New South Wales. So I think that's a long path and a proud path. And we hope that that's the path of presidents of the Royal Society of New South Wales will continue far into the future. I thought this morning I thought of something I should tell you, that I've thought of a real connection another connection between myself and Brisbane. And it connects all of the talk. It connects our Brownian motion and astronomy and so on. That I could have been an astronomer. I started my first research experience was earlier than I've told you. In my second year as an undergraduate in physics, I took up a vacation scholarship at Mount Stromlo Observatory, and it was run by a passionate, interesting, charismatic Dutch astronomer, Bart Bok. And everything was great. We had a wonderful experience, except that I had one misfortune, that because Bach believed that every astronomer should be an observer, we were rostered to do nighttime observing. And the observing was at the top end of the 74-inch telescope, now a wreck on the top of Mount Stromlo outside Canberra. But at that time, it was a functioning telescope, and the observing was done at the top end of the telescope. And what I discovered, particularly, that put me off the astronomical career, was that Canberra summers even the nights are long and very cold at the top end of the telescope. So I thought, this is not for me. I like my comfort too much. But it turns out I was completely misled, because astronomers, even a few years later, were all down in the bunker below the telescope. And now, of course, they're sitting at their screens across the world, and they're not allowed to touch the telescope anymore. So I was misinformed. But then I think, well, that was like one of these, invisible blows, on the path in the Brownian motions, one of those invisible blows that Lucretius talks about that set me off on a different path. If it weren't for that, I might have become an astronomer. I'd be telling you that now. But the invisible blows, of course, that set us along the way, they're not all bad news, of course. I have thoroughly enjoyed the path I followed, and I wanted to finish by just showing you this slide of some number of my recent and current collaborators, and they come from everywhere. I'm glad to see that they're looking happy, most of them, because I like people who enjoy their work. But they come from everywhere. They come from, I don't point them out, but they come from Germany, from Australia, of course, from China, from Vietnam, as I mentioned, from Taiwan, New Zealand, from Poland, many from Austria, from Belgium, and so on. It's a very international, a wonderful community to work in. And so it's been my pleasure to tell you something about my rambling path, and thank you very much for your attention.
Excellent. Well, we'll wait a second for the applause to die down. And yes. We note there's been quite a few people on the chat thanking you for your talk, Ian. So, and that worked, I think. It worked very nicely. I thought you were a bit rude to chemists. I was at King's College.
I'm very respectful of chemists.
Of course. And of course, the University College London was known by us as the godless College of Gower Street, which... So yeah. And again, we're all connected. It's wonderful. And I thought you brought that together very nicely. We do have questions. So thank you very much for people who typed in. Please add questions, and if I get to them, I'll put them to Ian. And the first one is from Trevor Bird. And it's something I've always wondered too. Why does Brownian motion lead ultimately in one direction, but not in circles or helices? Your examples, the first, the second, the third, started in a way, but then finished up along a kind of line. Why don't they go round in circles like most of us do?
Well, they get, I can't answer that really, but I mean, the mathematics is that the distance away is proportional to the square root of the number of steps. So they do get further and further away on the average. Actually, I wondered about that three-dimensional example, whether somebody had selected the realization so that they all stay within the cube. Cheating like that goes on all over the place in representations of things.
And of course, once you've taken a step in a particular direction, your new point of starting isn't the old one, which you've now forgotten. It's the point to the left or the right. So now we're in a new ball game of where we go from there. But I'm still not sure. But thank you, Trevor. Guy asks, sorry, I don't know Guy's second name. Asks suggestion on how do we present or extend presentation of multidimensionality, n greater than 4, I would have thought n greater than 3 works for me, and young minds and teachers of topography and so on. I mean, I think this was something you looked at, I think, in your last talk to the Royal Society. Yeah. How can we even start to think,
It is a very difficult question, isn't it? I struggle with the high dimensional illustrations for my talks and papers. So tonight I thought the Mexican hat was rather colorful, at least, but it's only two variables. So, this is not very convincing. So I don't know the answer, but if you find the answer, please do tell me.
It's all a mystery to us all. Ian Bryce has, and again, another good question that occurs to me and has done, and it's about time. Your scattering problems had time as an independent variable, but your UX has no obvious time. Is there time in there somewhere? Because we chemists, of course, never worry about time when we're doing our Schrödinger equations for atoms and so on. So what happens to time?
Yes, well, that's a very good question. I suppose the answer is that even in scattering, but in a bound state problem, such as in chemistry, or it's obviously you're not dealing with time, you're dealing with something that's static. But a scattering problem, the right way to think about it is that you're dealing with a steady beam of particles. So the experimenter, of course, looks at the steady state situation where you have a steady beam coming in and scattered at some angles, and you have detectors at these angles and so on. So there's no time in it. Of course, there is time in the Schrödinger equation, but you can look for solutions that are simple in time, a time harmonic or time invariant. So you take it out. Why? Why do you do that? To take out one of the dimensions. Otherwise, people who work in dynamical systems talk about, say, 3+1 dimensions, meaning 3 space dimensions, 1 time. It's a lot harder than just 3 space. So you take out time, if you can, where possible, to make life simple.
And is time special? I mean, we talk about time as though it is special, but is it just, if you've got 100 dimensions, 99 plus time? So is time really?
Time is always different. I mean, and even in relativity, special relativity, it's different. Time, I mean, it comes out in a natural way. You think you set up a steady state sort of experiment, so you're not interested in how it begins and ends. It's a steady state situation. It should make sense that you can look at it theoretically, just in terms of something that does not depend on time.
Thank you. Bob Marks, the editor of our journal, has asked, in fact, the question, I think that when you showed us that lovely cosmic background and you asked those questions, what are the answers? Is it really a realization of a random field? And if it isn't, what is it?
Well, it is pretty much. I mean, we looked at, there are different maps. Okay, so there are maps that some of the maps are severely distorted along the boundary. I can't quite do this, but if you can imagine now, you take a horizontal line through the center of my image. There's a lot of obvious rubbish in many of the maps along there. And why is that there? That's because we're looking through our galaxy. We're looking through our galaxy, and our galaxy is full of dust and so on. So if you start with those maps, you certainly find that it's not a random thing. They're very striking departures. Of course, you can see the departures in some sense, So this is where we started. We started with not being astronomers, not being experts, and not being closely connected to the communities. And what we didn't know is that they were going to put out new maps in 2018. So that set us back a long way. So I don't have a clear answer. We found recently some departures way away from the galactic plane, were interesting, but we think now that there are artifacts of noise in the detectors. So yes, randomness is where it's a random field as much as it should be a random field.
I'm tempted to ask another question, but I won't. I'll be very good. And I'll perhaps move on to a rather technical question from Herbert, who obviously see you well enough to ask questions. Ian, concerning your random flow through difficult media, we have in fluid mechanics a linear porous media equation, which is much used and accurate. Why can't you use it?
Well, we like to do what we're doing, I suppose. And that's an answer which is, true often in science, isn't it? We like to do what we're doing.
Thank you, Herbert, as they say. He asked another question, which I perhaps will ask at the end, because that's a general one. But Tona Stevenson, and so this is the last, perhaps the second to last question. Great talk. He notes that some of the instruments brought by Thomas Brisbane to Parramatta and used by Rumka are actually on display at Sydney Observatory, including a regulator, repeating telescope, and a dipping needle. And I wonder if they at the observatory know about our 200th anniversary. That's just a general point.
Yes, a very good point. A very good point. I didn't know that about them being on display at the observatory, but I'm always willing to learn new things, right? I've made that clear.
No, thanks, Tona, but that's good. And finally, if I may ask another Huppert question, how do you decide whether the hole is deep enough and you should go on to another hole?
Well, that's an interesting question, isn't it? I found that usually I get distracted by something new, and I've left the hole without really intending to leave the hole. I never intended to leave physics, actually. It's just that I never had quite got back to it in time to keep it alive.
And perhaps, I don't know if you find this, but I find I have multiple holes that I hop between, and some are more important sometimes and some are less. So if you're kind of really interested in things, you find yourself starting to get involved in a new hole. And of course, this is this problem of depth versus breadth, I guess.
Yes. Well, I wasn't giving a prescription for how to get the Nobel Prize or anything. I was giving a prescription for how to be in there for the long haul. You don't get bored if you keep moving.
Thank you very much. I think we ought to stop there. I think this has worked. I'm going to pass over to Judith to give the formal vote of thanks. But I've found your talk exceptionally interesting, so thanks very much, Ian. And we did have questions. People have come in on the chat room, and thank you very much for a lot of the thoughts from there. So I'd consider this a bit of a success. But to conclude this evening's proceedings and say ta very much, I'd like to ask my co-vice president, Judith, to take the stage. Thank you.
Thank you very much, Bryn. I feel very honored to have the opportunity to give this thank you, because I think it was quite an important talk we just heard. But I'm going to make you wait for a minute because I have actually 3 thank yous, and I'm going to save best for last. My first thank you is to our audience, both the audience who is listening now and for those who come along afterwards and pick this up in a podcast, or maybe some of you who want to hear it a second time. Audience, you've been great. The questions, the interaction, the chats back and forth, I think have added a dimension that we haven't had before, couldn't have, and shows that we're going to mine this new medium to make it something that really is useful for us. We do miss the wine beforehand and the face-to-face talk, but we've added some other things that give a depth to this kind of a communication. So thank you for being in the audience for our first and very important production. And I hope you did enjoy it, and I hope you'll tell others, and that we'll build an audience as we go for our online programs, something that I suspect will continue in the future, even when we are meeting face-to-face. Remember to read your emails, go to the website, find podcasts, replays of programs, and so on, to keep yourself up to date, lively, and in communication with each other. Ideas at the House, the COVID lectures, David Hush's musical performance that we couldn't repeat, tonight's lecture, all are there for posterity and for you to enjoy again. But how did it all happen? And that's my second thank you. I really have to name Lindsay Boughton, our webmaster, Stuart Midgley, our master of ceremonies tonight, and the one who has worked so hard on our webinars and Zoom programs, and our executive officer, Wendy Ennefelson, who have formed I was going to say a committee, but a bit more like a triumvirate, looking at the problems that were facing us in trying to suddenly put everything online and realizing that this was a major project of major importance to the Royal Society that had to succeed. And those three have been working just about full time to figure out the best way to use these new tools, to master them so that we would operate smoothly. Bryn has given the same judgment I would give. I think it was a great success tonight. And it really all was made possible by those three people, Lindsay, Stuart, and Wendy. And I'd like to hear your applause out there for them. Thank you very much. I can hear you from here. And now, best for last. I'm tempted just to read out the chat comments, and I hope that Ian is going to get a chance to see them because there are so many thank yous, some with quite a bit of detail about why people enjoyed Ian's talk. And in a way, it would be enough if I said that and added my own thanks and let you all, I was going to say go home to bed, but go in the next room and go to bed. But I really think a little bit of pondering on what Ian has just told us might point out some of the real importance of what he had to say to us. First of all, he laid himself bare. He really did give us President's reflections and allowed us to see a bit of the real Ian. Some of the lines that particularly made me think, that's the man I've been working with for several years. And he didn't know perhaps how much he was showing. But when he talked about Jeremy Bentham welcoming Jews, Catholics, and women, it is a mark of the man, Ian, that he thinks that's an important thing to tell us. And it is very important. It's important to us as human beings, but it's an important characteristic for the Royal Society as well. We saw the human side of him when he let the cold astronomical nights in Canberra affect his career decisions, very sensible too. And a different side of the human when he emphasized how much he enjoyed his colleagues. But what about this random path he took us down? Random, without aim or purpose. Middle English from Old French, meaning rushing movement or disorder. The drunkard perhaps was disorderly, but Ian on his random path, I thought did something quite different. He went a little bit this way and a little bit that way, but each time turning to a new opportunity, which he later talks about in his metaphor with the whole. But we see that those opportunities have developed very important ideas in his mathematics and science, but very important ideas that he has brought with him to the Royal Society. And we can say that concisely by looking at his Secrets of a Long Path, which it could have been called Secret of the Royal Society of New South Wales, of which he has been president. He says, don't keep digging in the same hole, cultivate widely. There we see the value of listening to people from other disciplines, asking questions from a different discipline point of view to see where there are challenges, reciprocity of ideas, transfer of information and understanding from one field to another. One of the really important things we do in the Royal Society. And on that same theme, we saw the value of the arts to Ian. He's quoting Lucretius, for goodness sake. Jeremy Bentham, Wozniakowski, which he took the trouble to learn to say properly, and I admire him for that. But his second point on the long path, be willing to learn new things. And isn't that also what the Royal Society is all about? Pushing knowledge to the new frontiers, being interested in what's new and coming along, and learning from each other as we go, which gives us the third point about the Royal Society. Be a good collaborator. Get together, have fun, teach each other, learn from each other, support each other in our endeavors. So the random walk that Ian took us on was in no way just rushing movement or disorderly. It was very orderly indeed and had a great purpose behind it, to let us understand him as a person, his career, ideas for those who are forging their own careers about how to move forward, and also an insight into his leadership of the Royal Society. So I want to thank him very much on behalf of all of us for his leadership of the Royal Society and, sorry, juggling notes, for his leadership of the Royal Society, which is not over yet, I emphasize, and for his regard for liberal values, people, our sharing and understanding each other, and for the lecture tonight and the very considerable work he put into it. So he not only receives our thanks, but medal from the Royal Society, which I hereby present to you, Ian.
Thank you so much.
People at home can, I'll just hold it there with my fingers, which look gigantic up here, but because when we give this to each speaker at the OGM, the audience never gets to see it. It's a version of our seal. It's very handsome indeed, and you deserve all the symbolism that this gives to you, with our gratitude for a really scintillating, enjoyable, humorous, and deep conversation this evening. Ian, thank you very much.
Thank you, Jim.
Again. And with that, I thank all participants, which means many, many, many of the audience, more than usual even. And thank you for your attendance. We'll see you at the next event. Keep your eyes on the website. Good night, and thank you very much. Good night, everyone.
Thank you.
Thank you all.
Thank you.